Hello everyone, this is Alla Basha, physical science teacher from Pre-Assessment High School. Welcome to my class. Today we are going to discuss about force, gravitational force and gravity. So in class 8 we discussed about the force. What is a force? Force is a pull or a push which acts on object with or without being contact with it. There are two types of forces are there. Number one, contact force. Contact force. Number two, non-contact force. Contact force, non-contact force. Contact force is nothing but the force is acting on a body, actually touching on it. Non-contact force is nothing but the force is acting on a body without touching it. Contact force examples: muscular force, normal force, tension force, like this. But non-contact forces are three are there. In that, electrostatic force, magnetic force, and gravitational force. About these all forces we discussed in class 8. But now here we are going to discuss about gravitational force in detail. We are going to discuss about gravitational force in detail. Gravitational force. Gravitational force. So what is gravitational force and what is gravity? So gravitational force is nothing but the force of attraction between any two bodies in the universe. Gravitational force is nothing but the force of attraction between any two bodies in the universe. For example, the gravitational force is acting between the moon and the earth. Here moon is revolving around the earth due to gravitational force. But the mass of the body plays a key role here. The object which have more mass, they have more force of gravity. The object which have less mass, they have less force of gravity. But here the other force is acting between the moon and the earth, that is centripetal force. At the same time, earth also revolving around the sun. Here also there is centripetal force in act. Centripetal force is nothing but the force which acts toward the center in a circular path. Here, one more also is there, what is the gravitational force? Universal gravitational force. This universal gravitational force was defined by the scientist Sir Isaac Newton. So we know the story of the Sir Isaac Newton. He only first discovered about the gravitational force. So what is the gravitational force? Gravitational force on the earth is nothing but the objects which are attracted toward the earth nearby the surface of the earth or just above the surface of the earth. But Newton's observations are different. He observed that why that apple falls on his head. Why does this apple not going to upward? Then each and every object coming toward the earth means. What about the stars? Why the stars are not falling toward the earth? What about the moon? Why the moon is not falling toward the earth? So by observing this all and by doing so many experiments, he decided that in the universe between any two bodies there is a force of gravity. Between any two bodies there is a force of gravity. This force he called as universal force of gravity. Universal force of gravity. This can be denoted by F suffix G. Universal force of gravity. And he is given that law of universal force of gravity. What is the law of universal force of gravity? For example, any two bodies in the universe. Imagine that any two bodies in the universe. Here is one mass, here is another body. So mass of this body is m1, mass of the second body is m2, and these two are separated by the distance d means. The force of gravity is directly proportional to product of the masses. Product of the masses. And the force of gravity is directly proportional. Force of gravity is inversely proportional to the square of the distance. Square of the distance. Force of gravity between the two bodies is directly proportional to mass of the product of the mass of the bodies and inversely proportional to the square of the distance. So from this 2 we can write as universal force of gravity between any two bodies is directly proportional to mass, the product of the masses and inversely proportional to square of the distance. If you want to use gravitation constant, proportional constant, F is equal to G m1 m2 by d square. Here G is known as universal gravitational constant. Universal gravitational constant. This universal gravitational constant was found by Henry Cavendish. He said that the universal gravitational constant value taken as 6.67 into 10 to the power of minus 11, 10 to the power of minus 11 Newton meter square by kg square. So this is the G value, it is given by Henry Cavendish. So now let's define the law of universal gravitation. The law of universal gravitation force is nothing but the universal force of gravity is directly proportional to mass of product of the masses and inversely proportional to square of the distance. Let us see a small video about the law of universal gravitation. See here, a blue one and green one are the two masses separated by the distance d. Let us know about it.
Law of universal gravitation. In his law of universal gravitation, physicist Sir Isaac Newton proposed that every object is attracted to every other object with a force directly proportional to the product of the masses of the objects.
Means it is the law of universal gravitation states that it is directly proportional to the product of the masses and inversely proportional to the square of the distance.
And inversely proportional to the square of the distance between them. Newton's law of gravitation can be expressed in an equation. Fg is equal to g multiplied by m1 multiplied by m2.
Here m1 is a mass of the first body, m2 is mass of the second body. Here they took r square. R square is nothing but the distance between any two bodies. From the center so they can take it. That is why they can take it as they are taking as r square.
Whole divided by r square, where Fg is the force of gravity between two objects of mass m1 and m2. R is the distance between the center of the two masses, and g is the gravitational constant. The value of g was determined by scientist Henry Cavendish as g is equal to 6.67 times 10 power minus 11 meter square per kilogram square. The law of universal gravitation implies that the greater the masses m1 and m2, the greater the forces of attraction between them will be. If the mass of one object is doubled, the force will be doubled.
See what they said here? Universal force of gravity states that it is depending on the masses only. So just we can write here the formula. F is equal to G m1 m2 by d square. Okay, what will happen if the mass of one body is doubled to the force of gravity? Let us imagine that m1 is equal to 2m1. Means here first body is doubled. Mass of the second body remains like that only. m2 we can keep it. If we and distance same only. If we substitute this value in the f is equal to g into m1 place we get it as 2m1 into m2 by d square. So from this we can write as 2 into g m1 m2 by d square. So from this it becomes 2 times. When the mass of one body is doubled, the force of gravity between the two bodies become 2 times. 2 times will increase. If two bodies will be doubled means the force of gravity become 4 times. There. So from this we can say that the universal force of gravity is depending on the masses of the bodies. At the same time, another one also is there, that is the distance. So it is inversely proportional. Nothing but force of gravity decreases with the distance is increasing. Force of gravity increases when the distance is less. Means more distance, less force of gravity. Less force of gravity, less distance, more force of gravity. Let us do that one also. For example, the d value taken as half. D distance will become half means what will happen to the force of gravity? So from this F is equal to G m1 m2 by d square. D value here half, d by 2 square, half nothing but d by 2 whole square, that is equal to F G m1 m2 by d square by 4. Nothing but it is become as 1/4. G m1 m2 by d square into d square by 4. Means a half distance. When the distance become half, the force become 4 times increased. Means the distance is decreasing, force is increasing. Okay, let's come to another some points. Now, from these points, we can match this from the statements and gravitation. See, for first point here, greater distance between the objects. When the distance is greater between the objects, what will happen to the force? So, greater distance.
Excellent.
Weaker force of attraction. Force increases, force decreases. Next, mass of one object is doubled. If mass of one object is doubled, force also become doubled. Where is the force is doubled? Here.
Excellent.
Next one, both masses doubled. When the both masses doubled, the force become 4 times. The force become 4 times.
Excellent.
What the pulled? Next, mass reduced by half. So when the mass reduced half, force also become half. So here mass reduced by half. Here force reduced by half.
Excellent.
Last one is for us. Greater mass, greater the force of
Excellent.
greater mass, greater by the force of attraction. See here, greater the distance between the objects, weaker force. Mass of one object doubled. force also doubled. Both masses doubled, force become quadrupled. Mass reduced by half, force also become half only. Greater mass, greater force of attraction. So this is a universal force of attraction between any two bodies in the universe. Okay, then what about gravitational force of the earth? What about gravitational force of the earth? Now, mass of the earth is taken as m1, mass of the earth taken as m1 is equal to capital M. Okay. Let us imagine that an object is there on the earth, mass of the object is small m. Because if we compare the mass of the earth to the objects, that is very less only. Then universal force of gravity between them. F is equal to G. M1 place we get it as capital M. M2 place we get it as small m. The distance of the object is nothing but radius of the earth. Radius of the earth. So what happened here? G m by r square. In this, G is universal gravitational constant. M, capital M is the mass of the earth and small m is the mass of the object on the earth. R is the radius of the earth because we are taking the distance on the earth means it is taken from the center of the earth to surface of the earth is taken. So that is R square. Now according to Newton's second law of motion, if you transpose this M to the left side, F by M is equal to G M by R square. Here, according to Newton's third law of motion, F is equal to ma and A is equal to F by M. A is equal to F by M. So, we can substitute that F by M value from that equation. So, A is equal to G M by R square. So, here A is nothing but gravitational acceleration. So, gravitational acceleration we can denote by the letter small g, that is equal to G M by R square. From this what we can conclude, mass of the object is not a point here. Mass of the object is not a point here because mass of the object by force by mass is taken as g. So, irrespective of the mass of the object, the gravitational acceleration on the earth is same. Means even it is a lightweight object or heavyweight object, gravitational acceleration is same. G is equal to G m by R square. If we substitute the universal gravitational constant value, mass of the earth value, radius of the earth value, we can get the G value as G is equal to 9.77 meter per second square we get it. 9.77 meter per second square. So by making rounding off, we can get this one as 9.8 meter per second square. So this is the gravitational acceleration. This is the gravitational acceleration. So gravitational acceleration of the planet is depending on mass of the planet only. If the mass of the planet is more, there will be more force of attraction, more force of gravitation. Gravitational acceleration will be more. If the mass of the planet or celestial body is less, gravitational acceleration also will be very less only. For example, if we compare the gravitational acceleration of the earth, to the moon and earth means on the moon there will be less gravitational acceleration will be there. How much you know? 1/6. Let us see a small activity about the gravitational force. This is depending on universal gravitational force. Universal gravitational force. Here there are two bodies are there, M1, M2. Mass of the first body is 2 billion kg. Mass of the second body is 4 billion kg. And the two are separated by a distance of 4 kilometers, then between the two bodies there is 33.4 newtons of force is acting. Then let us try to increase the distance. If we increase the distance double around, previously it is 4 kilometer distance is there. Now there is 8 kilometer distance. So because of this reason, force becomes 4 times reduced. 8.3 only 33.4, that becomes as 8.3. Now let us try what will happen if we increase the distance. If we increase the mass, observe it. So mass of the first body is doubled. Force also requires double only. Now mass of the second body reduced. Still half means 16.72 kg. So universal gravitational force is depending on the masses and distance. Let us try. Oh, 9 billion kg. Because of that, 150.2 newtons of force is acting on it. Now, both masses are increasing. 337.9 newtons of force is acting on them. Okay, right. Let us discuss another one. Gravity and springs. Here there are two springs are there on the earth. If we keep some mass, fix some weight to that, we know that what is the mass and what is the weight. Mass is nothing but the body which contains in it, but weight is nothing but the force of attraction toward the earth into mass, that is weight. So here I am keeping certain weight to the spring. When I hang certain weight to the spring, there will be some stretch in the spring. So here the thickness of the spring is up to 3 points are there. What will happen if I increase up to this level? So the stretch is decreased. So here gravitational force is acting less on the heavy bodies. When the spring size is reduced, more force of gravity is acting on that. Okay, let us try. And now 250 grams I keep this one. 250 grams weight if I hang there, stretching the spring is more. Now let us go to another planet. Now here this is moving. We don't know what is the sun that I give here. This is moving. See what happens here. What is the meaning of this one? You know, when we give some weight to this one, actually up to this one is length, but up to here it gets stretched due to gravity and this thickness of the spring. It become. Now let us go to another planet. Small planet or satellite. We can go to moon. If we go to the moon, what happens here? Same masses. Same masses. Both springs are having same mass, so they will be same. Next, if I increase here, now if I go to Jupiter, if I go to the Jupiter, the gravitational pull is increasing because always it is gravitation acceleration is depending on the mass of the planet. Due to this one, it is having more. So from this we can conclude that gravitational acceleration is depending on the mass of the planet where we have. So from this we can say that weight can be changed from planet to planet, but mass doesn't change. Mass is constant, weight is changing because weight is depending on the gravitational acceleration. Weight W is equal to mg. According to force formula, weight W is equal to m into g. So here m is nothing but mass of the body, g is nothing but gravitation on the planet. What is the gravity? So just now I said what is the gravitation of the earth? 9.8 meter per second square. But the same time if you go to the moon, it is proved as 1/6 of the earth. 1/6 of the earth nothing but 9.8 by 6. 9.8 by 6. So our weight decreases when we go to, if we go to moon. Our weight increases if we go to Jupiter. Now I am going to another planet. I am going to another planet without knowing. See what happened to the Jupiter? Jupiter stretching, this one is there, but if I go to planet X, still some more is there. Means what is the meaning of this? Mass of the unknown planet is more. Due to that, more stretching is there in the spring. Now, if I right. Next we can go to one more. Motion in our solar system. See here, this is a model to scale. You can measure it. Now, this is a, we know that the sun, mass of the sun is more huge ball of fire, and it is the moon, earth. Now you can take this one. The motion of the sun, motion of the earth, motion of the around the sun. Let us try with the gravity and velocity and the path. See here what is going on. What is going on here, you know, the pink color path is the path of the moon because it is revolving around the earth. And here this part, this color white color is there, this is the path of the earth. We know that earth will take 365 days to revolve around the sun. Right? Now only if we take the moon and the earth. So here also between the moon and the earth there is a universal force of gravity is there. How the path is there, you see. Here this is green, blue color is the direction, force of attraction toward the earth, and this green color arrow mark is the direction of velocity. Direction of velocity. Okay. If you take fast lines, this is the path of the moon around the earth. Right. Now, from all these things we conclude that universal gravitational force is the force of attraction between any two bodies, and gravitational acceleration is nothing but the force of gravity on the planets. Force of gravity on the planets on its objects. Okay. Right. Let us clear this one and we can go to another point. Keywords, what we discussed up to now. So here we discussed up to some words in that mass, distance, force of gravity, universal gravitational constant. So here, what is the mass? A physical quantity expressing the amount of matter in an object. Mass is a physical quantity expressing the amount of matter in an object. Then distance only we know. The distance is nothing but the extent space between two objects or places. The extent space. So the red mark shows the distance between the two bodies. And force, the physical quantity that changes the state of an object. Next, force of gravity, the attraction attractive force experienced by an object attractive force experienced by an object due to gravitational attraction by a bigger object. Here, this violet color is the bigger object and the green color body is the smaller object. So there will be force of gravity more towards this one only. Next, universal gravitational constant. The universal gravitational constant relating force to mass and distance in Newton's law of gravitation. So this is the universal gravitational constant value. This is given by Henry Cavendish. Here, there is some recapitulation is there that G value is given 6.67 into 10 to the power of minus 11 Newton meter square by kg square, and this is capital G you can take as a universal gravitational constant. F is equal to, this is a universal gravitational force. F is equal to G m1 m2 by r square, and here the distance, it is depending on the distance and the masses. Next, we can go to motion of our solar system. A question is given here to you. A 10 rupee note, a pigeon feather, a cricket ball, and a pebble are dropped from a certain height. Which of the following options give the correct order of these times taken by each to reach the height when arranged in a descending order? Okay, so here what we are dropping? A 10 rupee coin, note, pigeon feather, cricket ball, and a pebble dropped. And which of the following options gives the correct order of the times taken by each to reach the ground in descending order? Descending order means you can see the answer. Pigeon feather, later 10 rupee coin, afterwards pebble, last cricket ball. So these are all first. Here, why? Because feather and 10 rupee note reaches the ground somewhat late, because there is some other disturbance is there to that. What is that? Fluid friction. If there is no fluid friction, nothing is there. If you drop these four objects in the vacuum, four of them reaches the ground at a time. Because already said to you, gravitational acceleration is not at all depending on the mass of the body. If there is no other force. So already I said to you, if net force is zero, the body either remains in the uniform motion or at rest. Like that here also, if there is no other external force act on it, all four together reach to the ground at a time. Next, see this question. Which of the following is not true about the universal law of gravitation? The force of attraction between two objects is directly proportional to the product of their masses. This is we know already. This is true. Second one, the force of attraction between two objects is inversely proportional to the square of the distance between them. So this is also true only by d square is there. Next, the force of attraction between two objects is only depend on the mass of the heavier object. Next, every object is in the universe attract every other object with a certain force. So these are all correct only, but this is not correct, because the force of attraction between the two objects is only depend on the mass of the heavy object is wrong. It is depending on the both mass of the both objects. So this is the right answer. Next. Now, we may get a question. The force of attraction is there between each and every body, no sir? Then why can't I am attracted toward the wall of the building? And why this chair is not attracted toward the bench? For this reason, simply you can say that daytime, whatever candle if we keep, and we see the candlelight? No. At the same time here also. Why? Because the intensity of the light of the sun is more than that of the candlelight. That's why we are unable to recognize the flame of the candle from a long distance. At the same time here also, gravitational force of the earth is more on the earthly objects compare the force between you and the wall. Due to the reason, we cannot experience any force of attraction toward the wall. Now, see this one. The earth is acted upon by gravitation of the sun, even though it does not fall into the sun. Why? If the earth is if the sun is attracted all the planet towards it, but at the same time planets also attracted the sun towards it. But here mass of the sun is more. Due to that, there will be centripetal forces acting on the body, so they can take a curved path around the sun. They cannot fall into the sun. Next one. A stone is dropped from the edge of the roof. Then how fast it moves at the end of the fall? So a stone is dropped from the edge of the roof. Then how far does it move at the end of the fall? End of the fall, it has maximum speed because of the gravitational acceleration of the earth. Next we can go to another question. A stone is released from the top of the tower of height 19.6 meters. Calculate the final velocity just before touching the ground. Let us calculate this one. Okay, mass of the stone we don't know. So what is the reason here? It is dropped from the certain height. So from rest it is dropped. So initial velocity u is equal to 0. What is the height of the tower? The height we can take as the distance traveled by the body, 19.6. Okay. Next one, we have to find out v value. What is the v value? So we know that uniform accelerated motion equations. What are the three? V is equal to u plus at. S is equal to ut plus half at square, and v square minus u square is equal to 2as. In this, if we want to find out the final speed, we have to use gravitational acceleration coming towards the ground. That is, it is taken as 9.8 meter per second square. So if we substitute in this equation, v square minus u square is equal to 2as. V square value we don't know, so we give v square minus 0 square is equal to 2 into 9.8 into 19.6. That is it. V square is equal to, here 0 is equal to 0. 2 into 9.8. This is also become as 19.6 into 19.6. So v square is equal to 19.6 into 19.6. 19.6 into 19.6 nothing but square. V square is equal to 19.6 square will come. So square will be cancelled. Find the velocity of the body. V is equal to 19.6 meter per second before touching the ground. Like this, you can solve the problem by using universal gravitational force at the same time uniform accelerated motion formula and gravitational acceleration formula. Okay. Thank you very much.